In this video on logarithms, we're going to look at the relationship between exponential and logarithmic equations. We'll be looking at the log laws and the exponential laws that they're related to. We'll be simplifying log expressions using the log laws and solving log equations using the log laws to simplify the equation first and then using the equivalent exponential expression or equation to solve it. And then finally we need to make sure, because logarithms have domain restrictions, and we'll get to that when we look at log graphs, we need to make sure that we're actually getting valid solutions for our equations. So we'll be checking those things too. So you will have covered exponentials and logarithms last year in Year 11, and you can remember hopefully the relationship between the positions of the letters in the exponential and the positions of the letters in the log equation. The easiest way to remember it is that the exponential equation is an expression of a rate of growth. So the base is our rate of growth. How fast is this growing? So if we use the one down the bottom, if we have a quantity that is doubling, so our base is 2, that is doubling each time period, and we go for 3 time periods, so say it's doubling every year, and after 3 years we'll have 8 times the quantity that we started with. If our growth rate is 10, so it is multiplying itself by 10 each time period, and say it happened for 3 years and each year it multiplied itself by 10, we would have 1,000 times the quantity that we had at the start. So the logarithm can help us to find, almost if you think of this as a time period, as how long it will take at a particular rate of growth to achieve this particular number. So for our log equation here, if something is growing at a base rate of 2, so it's doubling every time, and you end up with a quantity of 8, how long did it take, how many time periods were required to reach that quantity of 8 if it was doubling each time? And this one you can read as, if the quantity is multiplying by itself 10 times for each time period, and you end up with 1,000 of them, how many time periods was that? However you remember it, you do need to be able to write an exponential equation in its equivalent log form, and also a log equation in its equivalent exponential form. So you need to be able to swap between these two. And the reason you need to be able to swap between the two of them is that often you'll get log equations that simplify down to log of something is equal to something, and the only way to solve it from there is to write it as its equivalent exponential form. So if we look at this first question here, where we're asked to find the value of x, solve for x, so find x's value, what we need to do is think of this in terms of its exponential form. You can think of it in terms of a growth rate. If something is multiplying by itself by 4, you end up with 16. How many time periods is it? But most people will write it in its equivalent exponential form. So if we colour them up, we can go ahead and write it in its exponential form. And then we can solve it from there. We can write them as both with the same base. So 4 to the x is equal to 4 squared. You know 16 is 4 squared. So therefore x is equal to 2. It's a similar idea with this second one here, except this time we've got a large bracket as our final quantity. So we write it in its equivalent form, and then we solve it for x. So 2 cubed is 8, and then if you subtract 5 from both sides, you get 3 is 2x, and then x is 2/3. So this process of changing or writing a log expression or a log equation in its equivalent exponential form is a really important skill to have. In Year 11 you would have looked at the log laws, and they're more log patterns rather than log laws. So I have the 3 main patterns that you need to remember here. as well as two important values. So the first log law, if you take the log of a product, it's the same as the sum of the logs of the two individual factors. And its equivalent exponential law is this one. If you take the log of a quotient where one number is divided by the other, it's subtraction. This is the one that causes a lot of people a lot of problem. We'll talk about that more in a minute. If you are taking the log of some number raised to a power, it's the same as multiplying that log by the power value, which is a bit of a weird thing. If you want some more information about this and you want a full explanation of how these things break down or how these things are put together from scratch, Eddie Wu has some good videos that go through it from scratch. So if you're interested in how these laws actually work, take the time to watch those videos. We don't have time to go through them now. So that's Eddie Wu. And finally, our two special values for logs are directly related to their equivalent exponential forms. So let's use some log laws to simplify some log equations. So we're going to express each of the following as the logarithm of a single term. So we're going to use the log laws to do that. Now you'll notice that some of the terms that we have in our expressions here have leading coefficients. So there's a number at the front. And there's a 3 here, we've got -4 here, we've got the 4 here and the 2 here. Now none of our log laws started with a number at the front. So our first thing that we're going to do is we're going to use the log law that says when you multiply a log by a number, it's the same as the log raised to that power. So you can see I've taken the 3 from the front and now it's written as a power. Now we have log of something plus log of something else. So the bases are the same, so we can use our log laws. And so we've got a log plus a log, so that will be equal to the product of those two things that you were finding the log of. So we multiply these two together and we get y to the 4 on 3. So let's do the same with this one over here. We're going to use the log law to move the 4 here to become a power and the 2 here to also become a power. Now we have logs of all the same base, and so we can apply the log laws where we will divide these two numbers and then multiply by this number. And then we will tidy this up, and we can tidy it up a couple of times and then end up with the logarithm of a single term. The most common mistake that people make using log laws has to do with the log of a division. And it's not so much the mistake that they make when they do the log of a division, but it's what goes on in their head when they see a division and a log together. Most frequently it's something that looks like this, where they have a division of a log, so log divided by log, rather than log of a division. And so what they do is they apply the log law that we've applied here to the expression that we've got here. And so they'll write log to the base 2 of 4, because 8 minus 4 is 4, which is completely incorrect. What you actually need to do is simplify the top line and simplify the bottom line. And it looks like this. And as you can see, when you bring the power out the front, you're left with log to the base 2 of 2, which is 1, and 2 times log to the base 2 of 2, which is 1. And so the answer is 3 over 2. So you need to be really careful with how you think in your head, what your inner monologue is around log of a division, so log of a division, and division of logs. Don't get caught out with this mistake. So finally, let's solve a log equation. So I've got a big log equation here. And so what we're going to do, we've got logs on both sides. They're all the same base. So I'm going to write the left-hand side as a single log of a single term, and I'm going to write the right-hand side as log of a single term. So this side is the addition of two logs, so I multiply the two things that I'm finding the log of. And this is also the addition of two logs with the same base, so I multiply what it is that I'm finding the log of. What I've now got here is log of something is equal to log to the same base of something else. And so therefore, we can equate the values that we're finding the log of. Because if log of this thing is equal to log of that thing, then the two things must be equal to each other. So let's go ahead, expand these out and solve. So I collect all my terms onto one side and I end up with a quadratic. When I solve that quadratic, I get two answers, 6 and -2. So now I need to have a look at my answers to make sure that they are valid solutions. And I do that by substituting the value for x in at all the points along here. So I can only take the log of positive values. So this one should be okay, but you should always substitute in to check. So let's have a check. If x is equal to 6, then that's fine. That's 18 plus 4, that's positive, that's fine. 6 plus 5 is 11, so that's a positive number. And 6 is a positive number, so that's fine. We then check with -2, and this could be problematic, might not be. So 3 times -2 is -6, plus 4 is -2, and we've already got a problem with this one. If it's -2 in here, that still gives us a positive number, but we also can't have -2 in here. So all we need is for one of these logs not to exist, for this to be an invalid solution.